I see. Okay, people are starting to show up.
Oh, you see people, yeah? I'm not seeing
11 per, yeah, the
yeah,
participant number
oh.
is going up. I guess it's 6. Should I start the introduction?
Yeah, you can go ahead and start.
Okay. Well, welcome everybody. Today it is my great honor and pleasure to introduce Dr. Arndt Schiel from the University of Minnesota. He originally did his PhD work at the Free University in Berlin and then joined the University of Minnesota in 2001, where he has been since. His research area is quite dear to my heart. It is basically phenomena and spatially, it's concerned with phenomena and spatially extended systems, in particular coherent structures, patterns, and nonlinear waves. He has won several awards, including the SIAM Crawford Prize and SIAM Applied Dynamical Systems, and 2 SIAM Outstanding Paper Awards, and a Humboldt Research Award. He's been very much involved with SIAM and hopefully with CAMES in the future. And now I'll pass it over to Arndt to talk about dynamics without phase space. Great, thank you.
Yeah. Thanks, David, for the kind introduction. And it's, of course, a pleasure to be here and talk about work, if only virtually, but still try to do my best to give you an impression of the things we've been interested in the past. So the topics we'll talk about here are joint work. Mostly started with Greg Fay he was a postdoc in Minnesota at the time. He's now back in Toulouse, and Bente from the Netherlands, who visited and worked on some aspects here. And Tianju, who was a graduate student who just graduated, congratulations, and is off to China. He just made it over. So the topic here is dynamics without a phase space. I'll have roughly 4 topics that I want to talk about, which is, I'll start with giving you a little bit of an impression of local and non-local equations, talk about the effects of non-locality, some phenomena, some models that might play a role, and try to emphasize the differences between local and non-local problems. I'll give an overview, very selective, from what I find interesting in terms of how we understand these equations, patterns, and waves in local systems. And then talk about the main, and the third part, the main results that we have, which basically built a toolbox for analyzing non-local equations, replacing some of these subtle dynamical systems tools without relying on a phase space. And in the fourth part, if I have time, I'll talk about some sort of limitations of this theory and extension, sort of what is really different in non-local dynamics. So after this first part, I mentioned a few model problems. Here is an example. These are neural fields equations that I sort of started studying. This is we have an action potential that is distributed spatially, where X could be Rn. It could also be some kind of feature space where you're grouping neurons by some kind of characteristic, how they're connected, and what these neurons do. They can fire, and they get stimulated by an input where they're sensing firing of other neurons through the sigmoidal input function. And the convolution kernel here samples all the inputs and averages them. And the natural tendency is to reset for a neuron. It's a very simple model. It includes some kind of translation invariance as a simple assumption, the simplest context. and one is interested in kind of self-organized features of such systems. One can adapt this model, make it a little more interesting by have some kind of somewhat artificial adaptation variable V, which resets these neurons here. When many neurons fire, they tend to be all in an excited state, but this V will cause them to eventually drop back to a relaxed quiescent state. So lots of other equations. Among the simplest equations that I want to mention here is Nagumo or Allen-Kahn equation, which has some kind of non-local diffusion type coupling with a pointwise bistable dynamics. So this is sort of a simple system, one of the simplest system with non-trivial here bistable dynamics, and some kind of distributed feature, non-local coupling. One wants to understand the dynamics here. Other non-local models arise when studying water waves or fracture dynamics. Here's one example arising in water wave problems. They often come up when one replaces some kind of simple dynamics in the bulk by some nonlinear boundary integral operators. And that's how these operators K come in, often involving some kind of Hilbert transform or so, that play back sort of bulk dynamics to the boundary. In all these examples, you see these models involve only convolutions. That's of course an idealization, but it helps us explain phenomena that one sees in actual systems that might not have this translation invariance, but with this translation invariant, one can explain at least long-time transients that one observes in models. Okay. So a little more precise here is an example, the Fitzian-Nagumo equation that is a local model for excitable media. So it has this bistable dynamics and this adaptation variable that you saw in the neural field model. When you look at this without the spatial coupling that exists here in the U, then it just relaxes to a quiescent state to U and V equal to 0. So that's the single stable equilibrium, but small perturbations, depending on parameters here, epsilon and A, can lead to like long transient excursions before relaxing back. The spatial coupling then can lead to prolonged sort of actually spatial temporal dynamics. It's a model that has come up about everywhere in non-equilibrium dynamics. Hodgkin-Huxley, simplified version of signal transmission along nerve axons, surface catalysis, calcium signals in muscle tissue, and many, many others. There is lots of non-local versions of this model where one replaces here the spatial coupling by some kind of, instead of this infinitesimal comparison with neighbors, what the Laplacian does for you, you're kind of comparing U to an average of neighbors, K is a probability kernel. That comes up in neural field models that I showed you earlier, and more general models of networks. Here's a few examples where you see these models. The simplest example is here, the Fitzian-Nagumo equation. This is a simulation where I'm starting with an excitation here in sort of a line. So U is on here, 1, and V is on in a region which is slightly lagging behind. And if I'm, oops, sorry. If I'm running the simulations, then I see how this propagation pulse here spreads out, but curls up at the end and produces a spiral wave. Similarly, when I do the same thing in the non-local system, God, sorry, I'm apparently not able to figure out my controls here. In the non-local system, you see that this propagation is much slower and leads to actually collisions here of these spiral cores. They grow again, collide with this reentrant segment. This is periodic boundary conditions, form 2 new open arms that curl up, and eventually they combine and just form a single traveling pulse, which travels slowly through the domain. And that's of course not the only dynamics you could see, but it illustrates a little bit the kind of qualitative differences you will see because of small quantitative variations in the dynamics sort of a more of a strange application. Strange because I think it makes me feel a little strange these days, in these days of social isolations. Looking at these videos of crowd dynamics makes you, I don't know, feel strange, or eerie, or longing for a better world. So people try to imitate this, these kind of dynamics. There was an experiment at a conference in Atlanta where they said, okay, this excitability possibility, you can mimic this by have a crowd stand together and just raise their arms when neighbors raise their arms. And then there's a recovery phase where they're not able to raise their arms. And if you run this, you do this, you see that. So there's a line, this is this yellow line that you're seeing here where sort of people hold up a yellow board, and on initiation, this line curls up, goes around, and forms a sort of spiral shaped pattern. Not great visibility, but I think the resources were somewhat limited. People have better resources in stadiums where this is, of course, known as the wave going around, this excitation wave going around the stadium to create a crowd atmosphere, right? So this is excitable media, one example where sort of these non-local couplings are of interest. And here's a simpler example where I'm removing this adaptation. This is a simpler toy model for many, many things, phase separation, signal propagation, again, and more recently also in machine learning clustering algorithms. Non-local versions, again, motivated by network models and non-local couplings, where you replace the Laplacian by a Gaussian, and discrete versions where this happens basically on a lattice. You can interpret these also as a non-local version where this convolution kernel just samples neighbors at discrete locations, right? At a lattice site plus minus EJ apart. This is nothing else, if you look at this, as the 5-point stencil for the Laplacian on a grid. And if you look at simulations for this, then you see that in the local case, so this starts fairly slow, and then it spreads out, the simulation accelerates, and have a little bit of an imbalance. Then you see that the local case enables fairly fast spreading, where in the end, black, which is the zero state here, wins over. Whereas in the non-local version, you see very, very slow propagation. And in this discrete version, you actually see faceting, where in the end, this propagation, the spreading arrests along lines that have 45-degree angles to the lattice. So if you look again, I start with somewhat random angles here, and you see it bulges out in this area and creates a new facet here at the bottom before it eventually all facets have 45-degree angles at which time you reach a stationary states. These phenomena, slow propagation or non-propagation, are usually referred to as spinning, and that's what I want to come back to in the end of the talk. So this is the motivation, these kinds of phenomena, simple phenomena, for studying coherent structures, traveling waves, pulses, spiral waves in these kind of dissipative equations. And I want to start with is a review how we usually do this. This is sort of textbook information. We teach this in undergraduate classes on dynamical systems, how one finds, for instance, traveling waves in the Nagumo equation that leads to a second order equation, a second order damped pendulum equation, if you wish, with a cubic nonlinearity. And one way to study is, there is many ways, is to write it in a phase space as a first order system and then draw pictures, find equilibria, linearize at the equilibria, find unstable and stable manifolds, and try to match these unstable and stable manifolds in order to find these heteroclinic profiles that you see up here. We do this by varying the speed c, which is of course exactly what gives you that speed of propagation that you saw in these last videos. How fast does this black region spread into the white region? So there's lots of tools here. The invariant manifolds you can do in phase space. You can compare where do these curves lie above, below each other. pointwise monotonicity methods. Of course, Poincaré-Bendixson is an extreme example using drawn curve theory in the plane. And exploiting all these tools is a lot of fun and gives you very strong results in the end on what these equations do. Here is a fancier application that is to the Fitz-Nagumo equation, trying to construct these traveling pulse solutions, right? In phase space, if you just look at the ODE without the UXX here, you have this, what I described as this large excursion. This is people raising their yellow board before they raise it back down, right? Lower it back down. When one looks at trying to find these pulses, that's the last thing you saw in the nonlocal equation, right? Just propagating as plane waves. One comes to this traveling wave equation, which is now in R3. So one has to construct heteroclinic orbits or homoclinic orbits for this three-dimensional ODE, which is a little harder. And what was developed for exactly this purpose is invariant manifold theory, slow manifold, singular perturbation theory, geometric versions of it. The first proofs, Carpenter-Hastings used sort of these geometric constructions, topological methods, or more like singular perturbation methods in order to find these homoclinic orbits. Here's a schematic illustration on what's going on from a more recent work, which I'll come back to later, by Hupkes and Sunstede, where they constructed these pulses actually in the discrete case, right, in the lattice case, where one tracks unstable manifolds, uses some kind of transversality of intersections, construct the green manifolds, slow manifolds, center manifolds, in order to, in the end, find a trajectory that does this whole excursion before it comes back. And that's in that prime variable, which of course comes from the traveling wave variable. So this is the spatial profile that you see up here, like in a time series plotted. Another example, very powerful tool in constructing solutions is center manifold reductions. So if you have a more complicated system, not just one or two equations, but a system, say in Rn, then in general, it'll be very hard to find, say, stationary or traveling wave solutions, which are described by this gray equation here. But you might be interested in such a system because it's a more realistic model, say, the Hodgkin-Huxley system, or a more complicated system that describes a Turing pattern formation or the Belousov-Jabotinsky reaction. And then in order to find solution, you might start near an equilibrium, near some kind of trivial, obvious equilibrium that you can compute just algebraically, and find solutions nearby. How do you do this? Well, this is an ODE, and you want to find small amplitude solutions. You do this by writing this again as an equation in phase space, W is U and V, writing a linear part, identifying the linear part, which is this V, and then there is a CV with the D inverse and the linearization of F, and a nonlinear part, which you identify which orders come up. You look at the linear part and say, what are the almost bounded solutions to the linear part? So solutions that don't grow exponentially, because at the end of the day, you want solutions that are bounded in this X variable. So you're looking for what's called the center subspace, solutions that neither grow nor decay, because decay would mean growth towards x equals minus infinity in time. So you focus on these solutions, the blue part, and say, maybe I can say something about the nonlinear equation. And there are theorems. These are called center manifold theorems, going back to the 60s. Kelly was one of the first person to formulate a really conclusive proof for this, that say, well, all solutions are described as a graph in this phase space. W lives in R2n. Here's the R2n. In this phase space, you have a graph over the center subspace. That's this blue line. The blue line could be, as in this example, maybe three-dimensional. A three-dimensional subspace, but this EH could be very high-dimensional. So you're reducing the equation by projecting this green flow, this green vector field down on this horizontal subspace to a lower dimensional equation, which you might be able to solve in the same way that we solved the problems in the previous slides. So you can, for instance, find these Nagumo-fronts in higher dimensional systems of equations where you do not have these kind of monotonicity properties, and therefore find solutions for small amplitude and then either choose numerical continuation or analytical continuation results to say something about solutions in more general cases. These kind of methods you can also use whenever you have some kind of one-dimensional structure. So instead of X, you might be thinking of the radius R and try to prove something in this case. So a step away from these simple dynamics was looking at these methods for elliptic problems. So when you look at this elliptic equation in a cylinder, in a strip with periodic boundary conditions, then you can do the same thing and write this as an equation in phase space, but saying my phase space now is infinite dimensional. It consists of all profiles at some point X in time, right? These are, the good functional analysis tells you should choose H1 and L2. And then you have what looks like an evolution equation in X. It's an ODE, okay, infinite dimensional. But of course, it's still an elliptic equation, so you can in general not solve the initial value problem. So you have a phase space, but you can in general not do dynamics. You don't have an initial value problem. Kirchgessner in the 80s showed that it doesn't matter. You can still do everything and reduce the vector field, if you want, to a vector field on a center manifold. And on this center manifold, the initial value problem is well posed. You get a nice vector field. You can do Taylor expansion, thereby construct solutions to this equation. So for instance, periodic solutions, homoclinic solutions, heteroclinic solutions, profiles that have limits as you go along the cylinder to infinity. So these could then be your water waves, your heteroclinic profiles, your traveling waves, or something now in a cylinder. So this is a step away from these traditional sort of point of view of a phase space with a nice flow to saying, well, all I need is a phase space and something that has good properties, some infinite dimensional equation. This has been tremendously successful. I have enjoyed working on problems like this for a long time, proving existence and understanding the structure of objects like spiral waves, where now this X here might be the radius, and the Y might be the angle, of target patterns that like send out waves where the Y might be now time and the X might be the radius. Defects in soft matter structures like striped phases, you can do local bifurcations, construct solutions, and then try to do global continuations. We've worked on this. Or in water wave problems, many people, there's a very incomplete list, just some names that are associated with problems that I'm mentioning here have contributed, constructing periodic waves or solitary waves in water wave problems. So this is sort of where I want to start, where we set in and asked, what do we do with non-local problems? And that gets me to the third part here of the presentation, talking about dynamics, as I explained them here, without resorting to a phase space. Constructing such profiles, solitary waves, invasion fronts, breathers, more complicated structures, using these same kind of techniques, but without resorting to phase spaces. What do we do when we don't naturally talk about a phase space? So here's a problem that we started with coming from these neural field equations. Look at an equation on the real line where you have some matrix, you can set it to the identity, lose nothing. A matrix convolution kernel. So the system has a translation invariant, so it makes sense to look for traveling waves, for instance, like profiles, like heteroclinic profiles. So these come up as traveling wave equations, for instance, in water waves. And then some nonlinearity. So the main assumption here is just translation invariance. You have a symmetry, not necessarily dynamics, although you might argue what's the difference anyway after seeing this here. The nonlinearity can have convolutions in there. It's in some sense smooth. This is technical to state, but it's a broad class of equations, pointwise evaluation, nonlinear function, convolution, compositions of those, and so on. You can even allow for bilinear, multilinear convolution operators, and so on. What we always require for this interaction, the nonlocal coupling, both in the linear part and in the nonlinear part, is it is by some smooth kernels, and the kernels are localized. The principal part in terms of regularity should be invertible. When you do this, you can, without writing this as an ODE, you can just talk about, well, let's look at my linear part that has a translation invariance. So linear equations with translation invariance I solve using Fourier. Now, since this k is exponentially localized, I can actually do Fourier transform in a strip around the imaginary axis. So I look for solution e to the nu x, and nu can be not just purely imaginary. And I'm computing this characteristic equation that tells me when do I have solutions of this form, meaning what are my candidates for bounded solutions on the linear part. That replaces my sort of linear algebra matrix characteristic equation that I find in the ODE context. So from this, I can construct a center subspace. These are solutions which are like e to the ILX, but with a polynomial in front only. So these are solutions that have sub-exponential growth as x goes to plus minus infinity. And this exponential localization guarantees that the set of these solutions is a finite dimensional subspace. A finite dimensional subspace in the space of solutions with weak exponential growth. So here the U can grow. The result Greg and I proved, appeared a couple of years ago in the transactions, is that there is a center manifold. We don't talk about, we just have this translation invariance, but we have a center manifold and it's diffeomorphic to this center subspace. And it sits inside the space of all functions. But on this center subspace, I can construct a vector field and a flow. I hope I can make this theorem really clear by here. This is how we think about this, right? You can say there's always a phase space. It's the set of bounded solutions. I just throw everything else away. You can always do this. As soon as you have a symmetry, you say, let the symmetry act on objects within reason, the bounded solutions. And the flow is then the flow is the action of these translations on the space of bounded solutions. And if you could differentiate, you would even get a vector field from a flow. But if you want to differentiate, you need to know something about that set of bounded solutions. Better be a manifold or something. Even if you want to do topology or something, Conley index talked about this. You need some structure. You need to know something if you want to compute topologies of invariant sets. You need to know something about these invariant sets. And that's what we say. We say, okay, first we construct our bounded solutions using just functional analysis. There is no flow involved ever. Then we find the flow from the action of translations and construct the vector field just by differentiating. So this is the schematics. We go from the center subspace to the space of solution, construct our set of bounded solutions. We have the action of the shift, and then we can project back down, and that induces a flow on this set of bounded solutions, which we can parameterize in some convenient way. Let's do an example. I claim this actually is easier in many ways than how we used to compute bifurcation theory, center manifolds. It does everything at a time. So this is my example. It's of course very simple. Here you would like to reduce by somewhat eliminating the fourth order derivative. And everybody can do this, of course, but I want to do this for a non-local equation, and you can compare results. in the non-local equation, these derivatives are replaced by conditions on moments. And these conditions on moments are that here the second derivative is non-zero, so I would need that the zeroth and the first moment to vanish. So zeroth moment should be 1, it's a probability kernel. First moment vanishes, second moment should be non-zero. So then in this case, I have, one can easily check this, I have a two-dimensional center subspace. You can verify using Fourier transform, whatever, that the set of solutions that don't grow exponentially is given exactly by functions of this form. A and B are real numbers. You take this, you stick it into your equation, you assume that you have a correction from your center manifold that is cubic, stick it in, compute, get an equation, say, okay, you have a polynomial on the right-hand side. Using moment expansions, you can see that psi has to be actually a polynomial. Compute that polynomial in terms of A and B. It's a short calculation, it's less than a page. Then you get psi. Once you have psi, you can use that action of the translation. This is psi. Use the shift solutions, differentiate, project back down, and here's your vector field. There's a reduced vector field on this model space EC for your set of bounded solutions. I argue this is somewhat simpler than constructing for a system, a four-dimensional eigenvector, do all the linear algebra to construct these projections and so on in order to arrive at, of course, the same equation. So you can do the same thing just using the moments of the second and fourth derivative operators, the Dirac deltas, and arrive at the same result. It takes a moment to get your head around what you're actually doing, but I hope I convinced you that it's actually not that bad. So in this example that I just showed you here, the question is, of course, what are the dynamics? So you see to leading order, say if the third moment vanishes, then you have a system that looks like a nonlinear pendulum. Do you have periodic orbits? For that, you would use something like another symmetry, Hamiltonian structure. This is something we studied with Bente. We said, okay, so these non-local equations, they often come from a non-local energy. So these non-local equations should be Hamiltonian, but Hamiltonian talks about a Hamiltonian on a phase space. A symplectic structure lives on a phase space. So where is that phase space? That's what we identify. The phase space is, of course, all functions. The symplectic structure is a convolution, double convolution integral over a quarter plane. And then there is some pointwise evaluations of convolutions. This symplectic structure, well, how do you prove this? Well, you just compute, right, once you know it, or you use some kind of non-local integration by part, which is something that's been developed recently, actually, in many contexts of computational algorithms for in elasticity and material science. There's been a lot of work in this direction. This is slightly different because we're also after symplectic structures and more here. Omega is in general degenerate. This is a convolution. If the convolution kernel has compact support, this is very degenerate, and it would be interesting to find out what this actually means. We haven't worked on this. Bente also found Lyapunov functions. If you look for traveling waves, if you have a damping term in this equation here, a traveling wave term, then you find Lyapunov functions, which is very useful. And sort of we are able to sort of basically recover everything we have for these local equations. A couple of words, I'm going to gloss over this. So the key is really finding ways to invert the linear part. So you're talking about operators that are multiplication operators and then convolution operators that are x-dependent, but have limits. This is what after using these exponential weights you find, and you want a Fredholm theory for such operators. So you do, again, that you have limits, so you can write down characteristic equation. And what you want to do is something that for ODEs goes back to sort of Palmer in the 80s, theorems that tell you Fredholm indices of these kind of operators with limits at infinity in terms of unstable dimensions, Morse indices. That's something that was done for these ill-post PDE by Robin and Salomon, independently also by John Malé-Perret, for delay equations, forward-backward delay. We do this here for these nonlinear, non-local equations with some contributions more recently from graduate students who showed that these results are actually sharp, Olivia, that you find Fredholm properties exactly when these asymptotic equations are hyperbolic, so no multipliers on the imaginary axis. Very similar ideas, except that, again, you can't rely on a phase space, so you have to sort of think differently. From this, you immediately get Fredholm properties of your linearized operator and the whole linear theory that you need for center manifolds. This has been done a little while ago, and there have been really, really interesting contributions by a number of groups here who continued this work in many different interesting directions. A group, Ming Chen and collaborators, Eric Wallen and collaborators, worked on applying this to water wave problems and not only doing local bifurcations, but trying to do global continuation results. And these local results are important because when you do global bifurcation, you always have to exclude that the branch comes back. And what you need there is uniqueness results. And we provide exactly these uniqueness results. So this is in sort of elliptic problems in a strip, or for Witham equations for like toy models for water waves, surface waves. Hamiltonian Hopkes with Willem showed that, a graduate student showed that, well, you can actually think of the space of all functions as a phase space. It takes a lot of work, it's really hard, but if you want to think about a phase space, you can. So everything is sort of equivalent. And what they do is they do use the Fredholm theory, which allows you to construct Green's functions and thereby a phase space, which again was known for local problems before. A contribution that I find really impressive is what Bente did together with Jan Bauer-Vandenberg, is they constructed actually the equivalent of a Conley index using this Fredholm theory and the local bifurcation theory and the Lyapunov functions, putting this all together to construct a global Morse complex equivalent to basically finding index theorem that guarantee global existence of heteroclinic orbits. That's still under review, a paper, but on the archive. So I have a few minutes and I go quickly over the other side, the quick and dirty side. These were center manifolds. What you can always try to do is say, who cares about these ODEs? I have a guess what solutions are. Let me close the argument. Here's an example. Constructing the Fitz-Nagumo pulse was done a long time ago in the 80s, Carpenter, Hastings, by various methods. Doing this for the non-local Fitz-Nagumo equation was major work. Did this together with Greg Fay, and I would argue the proof is in a way simpler. It's a long paper though, but it's almost self-contained. We use nothing. All we need is an exponentially localized kernel, and depending on where you start in the proof, some properties of the kernel like non-negativity and non-pinning assumptions. What we do is we replace all this beautiful, I love this, local geometric theory by something more direct. Instead of constructing these heteroclinics and matching these transversely, we use Fredholm arguments and bordering lemmas, bordering with wave speed parameters. Instead of doing slow manifolds, well, we construct a slow manifold. That's a center manifold. I showed you how to do this. Instead of doing an exchange lemma, which tracks manifold at the passage here, we use exponentially weighted spaces and gluing techniques. So this shows this a little bit, how we patch together profiles, partition of unity, and then use commutator estimates on these nonlocal equations. It's in the end a long piece of work, but it's sort of very direct. So a little piece of advertisement here. Another one is doing local bifurcation theory. Instead of doing sort of these local symptom manifold equations, you can just identify the leading order, which you can do in multi-dimensions, and say, okay, second moment being non-zero, I get something like the Laplacian, even without, so you need just a little crystallographic symmetry on the kernel. Identify the leading order problem in scaling, and then use a kind of a preconditioned Newton method to find equilibria here, solutions. That's a Tianzhu Tao did this in the first part of his thesis. Again, very direct, very short, much simpler of what I did using symptom manifolds a while back in an AMS memoir. But you don't get uniqueness this way. So I have a few minutes here to give you just a flavor of what's different. All the results so far deal with smooth solutions. I'm working in H1, actually I'm working in classes of function that are HK with many degrees of derivatives, because otherwise you cannot expand the vector field. If you have a smooth vector field, then you also have smooth solutions. So the solutions you should construct in a smooth space, so you get the vector field by repeatedly differentiating. So here is back to our favorite, very simple Nagumo equation. Since I don't have scale invariant, I need a little parameter here, the d, right? This is bistable, and I want to detune this A from a half. And for now, I'm using this Dirac kernel, so this is really your lattice Nagumo equation. At every lattice side, you have bistability, and this couples nearest neighbors in the lattice. And I'm putting this on the line only. And here's a simulation. What happens, here is pinning, and here is not pinning. So I'm varying my parameter a little bit. Oops, sorry, this was supposed to run, it wasn't running. When I vary the parameter just slight little bit, 10 to the minus 5, I see this ratcheting motion. I see the front hopping through the lattice. Lattice has size 100, times are actually 100 here. So the front actually takes off pretty fast. So the bifurcation diagram is that the front, in terms of this detuning here, is first doesn't move, and then it takes off with mu to the 1/2. What that is a saddle node, and you can make this very precise, this saddle node asymptotics. You can compute this coefficient. It's been known for a long time that in these nonlocal equations with a Dirac kernel, you have zero speed generically, and then a square root type takeoff very fast of the front, where it tries to make up for the zero speed that it had for all this time. Now let's replace that Dirac kernel by a smooth kernel. Sorry, forgot this one here. So the idea, and that's what really people think about pinning as this front here being stuck at inhomogeneities. The lattice really is spatially periodic inhomogeneous. Now, when you replace this by a smooth kernel, what you see is different phenomena. You still see pinning, although the pin profile looks different. When it depins, it moves extremely slowly. So I'm detuning here by 10 to the minus 2, and the times are very large. This is 600. It's a little bit of a small font here. So what you see is, in a smooth kernel, the speeds overall are much slower, and the takeoff is mu to the 3/2. And that we show this generic for localized smooth kernels. Well, we didn't quite prove this. Let me tell you a little more about this. The pinning was known for a long time. This was results by Bates and Chen and a series of results where they showed if you have a positive smoothness kernel, then you expect for D, when D is small, to have profiles that have exactly one jump. And these are pinned profiles, meaning there's a whole range of A values where they will not propagate. And here the reason they can't propagate is because you have to jump. In order to move, the derivative in time would be a Dirac delta, and the right-hand side, these are all good functions. There is no Dirac delta on the right-hand side. So jumps cannot propagate. So this is again why this can't move. What we showed is these asymptotics for rational kernels, generically for rational kernels, explicitly for these kernels where you have a very simple Fourier transform, where you find asymptotics that are 3/2. So very different asymptotics. And this is I believe, a very interesting results with lots of consequences. We've done a lot more analysis on this. The analysis is sort of a slow passage through the fold again, which Tao, my graduate student, has now generalized to more general kernel, not just the rational kernels. And we did this also for kernels where you have sort of less smooth kernels trying to homotope to this Dirac kernel. And you see that these asymptotics actually get worse. You get higher powers. It gets even slower. So there's a lot of interesting question here that we have not been able to answer. There's some numerical studies, but I invite you to think about this. Like, what does the kernel tell you about the dynamics, pinning, depinning regions, and then as a consequence, the spiral wave dynamics? Because whatever you saw in these first simulations on Alan Kahn and spiral waves is absolutely caused by exactly what you saw here, the pinning and depinning phenomena that I described. Without going too much in detail for the sake of time, let me just sum up here. So I hope I convinced you. It's sort of fun to think about dynamics as just a group action. Who needs a phase space? Let the group act and describe the dynamics. And if you want a vector field, you can always differentiate. You can reinterpret everything you knew about dynamics using functional analysis to some extent. And sometimes reading those papers that people wrote with a lot of insight about local equations. And there's a lot of interesting phenomena that we don't even begin to understand. There's a lot of papers, they're all on my webpage. Thank you so much for hanging in here. That was it. Bye. Thanks. I'll take question. So I have a couple of questions here in the chat. I don't know, David, should I just start answering, or did you want to say something?
Go ahead. There. Maybe it's, you just take off. You just do your thing.
So I have a couple of questions by Tom Hillen, who asks about like, so are non-local problems, and are they now easier, in some sense easier than the differential operators? And in a way, sort of the convolution is a compact operator. And well, you know, it depends on what you want to know, right? In some sense, they're easier because it's compact, but the problem, in a way, they're harder because, of course, the derivative is not compact, but the resolvent is compact, at least locally. So the time evolution is compact. So if you look at what can happen in time, it's much simpler. So the set of solutions asymptotically in time that you expect in differential equations is much simpler because you have this smoothing and local compactness property. And I showed you this in the convolution case where you have these pinned profiles and all sorts of complicated profiles that you can get, right? The ones I showed you, these compactly supported, these pinned fronts, they Leaf and Bates and Chen and others have shown this to very, very complicated structures of the set of equilibria. On the other hand, I was trying to argue when you do bifurcation theory or so, you can replace a lot of what you know about differential operators by equivalent tools for non-local operators. There is a second equation by Tom who asks, well, that's a question we actually studied a lot. When you say, okay, you take a non-local equation and you, in some sense, let it converge to the lattice convolution. What happens? Well, there's two parameters, right? There is a small parameter, which is the depinning parameter mu, and there's a small parameter, which is your limit. For every fixed epsilon in your limit, you see the smooth asymptotics as long as you have the convolution. For every, but if you fix your operator and let epsilon go to 0, of course, you recover the Gaussian. So in practice, when you look at this, you see a crossover. When the dominant term is just the lattice system, you're going to see the lattice result with the square roots until very, very close to the pinning, where you see a crossover in this kind of mu to the 3/2. So we measured this. It's really hard to measure. Did a lot of simulations and continuation, numerical continuation. And yes, you see this, but again, right, lots of things that one could say more about, no analysis. Interesting question from Corey Brown also here. How does this relate to sort of the kind of non-local operators that you might see in Koopman operator theory, sort of when you have a non-local, when you're pushing forward measures and so on? I don't know. I don't really know. So the focus here really has been spectral theory here in the context of coherent structures. And sort of the spectral theory that so spectral theory I'm talking about in context with Fredholm properties and identifying limits of essential spectra and so on. And this is of course exactly what you're looking for when you're studying Koopman operators. I want to go out on a limb, sort of some of the problems here that we're studying when we're saying x goes to infinity, they're related to going, in the case of the Koopman operator, to very fine scales. And these are much harder. I think that's fair to say, because you're lacking this kind of asymptotic translation symmetry unless you have some kind of scale invariance when you're studying this. And if you think this is not saying much, then you're probably right, but this is how I kind of make peace with this connection.
So
I don't have any other questions here in the chat. I think.
Oh, I can't see them, so.
You can't see them?
Yeah,
I can see them, and I can promise you I don't see any other questions. I'm not hiding anything here. So.
Okay. Well, thank you very much. That was a very interesting talk. Hopefully we can get together in person sometime.
Oh yeah, we wish.
In the near future, not too distant future.
Yeah.
It was very good to see you again.
Yeah, thanks, David. Good to see you, and thanks everybody for coming here. Bye-bye.